So let's talk about the way that light can look through a glass. And so I have a glass full of water here. And when I do this, first of all, you can look and see that the whiteboard behind it actually kind of shrinks because of the way that the light passes through the water differently. You can see that the box that's on the table, it also appears smaller, even though you can see the edge of the box out the left-hand side of the glass. You can see the entire box inside of the glass of water because of the way that light will bend a little bit inside of water. And so if I take a straw and I put it in there, it looks different inside the water as opposed to outside of the water. It looks a little bit larger while it's inside of the water and smaller while it's outside of the water. And so when you pass light through from one substance into the next, it changes the way that you see things. And so this is the premise of what we're going to be working on when we're talking about Snell's law. So when we talk about how the straw looks different in the water, or anything from behind looks different coming through the water, it's because of this quality called your refractive index. And your refractive index is a comparison of the speed of light in a vacuum to the speed of light in any given substance. And so the speed of light in the vacuum is as fast as you can go. Putting it in a substance, there's more particles, and so it'll always slow the light down. So when you take the speed of light in a vacuum and divide it by the speed of light in the substance, that will give you your n value. The slower that the light goes in the substance, the more times it would fit into that, and the bigger your n value. Most n values that we'll encounter are between 1 and maybe 3 or 4. If you're getting up toward 4, it's slowing down quite a bit. So the way that we see this written is n equals c over v, and we have to keep in mind that c is going to be the speed of light. It's a constant, and we will use 3 times 10 to the 8th meters per second for that. So when we're talking about an n value, the higher the n value that you have, it means that the speed of light in that substance is getting slower and slower and slower. So if you take a look at Snell's law explains a little bit mathematically of why you see something different from the air to the water, or really any one substance to another. And so what happens is, this is what Snell's law looks like. It's n1 sine theta 1 equals n2 times sine theta 2. And so if you have two different substances, let's say in this case that we have air and water, we take the n of air, and we just talked about that in a bit ago, and then times sine theta of the angle that is made with the perpendicular. So from this straight up and down dotted line, the angle that goes out from there. So you take the sine of that angle times the n1 is equal to the sine of this angle that's made inside the next substance, so in this case water, times the n of water. And so when you multiply those two and you multiply those two, they end up being the same. And so as n goes up, your theta will get tighter and tighter and tighter. And the difference between the n2, the greater the difference in the angles as well. So if I take this laser and shine it down this line that I have here, it's a little bit tough to see, but if I bring this down the line here, you can see that it bends and goes through the block. And it's not quite as straight as, the line's nice and straight, but it's at a different angle than how it comes into the block. And so I'm going to take and put a protractor on both sides, and we can measure that. So now that I have a protractor on here, I can shine my laser down that line again, and it's coming straight down the line. And you can see that that as it crosses the end there, and again we're going from the perpendicular line here, and so we can go over 10, 20, 30, about 33 degrees is where it's coming through over there, right about here. And so up here I've got 45 degrees. Down here, 10, from the 90, I'm going to count over 10, 20, 30, I'm right at about 33 degrees. So now that I know my measurements in here, I know that my theta 1 is 45 degrees, my theta 2 is 33 degrees, I can figure out what the n of the block is. And so n of air is always going to be about 1.00. In actuality, it's 1.0003. But for everything that we're doing, there's no purpose in going that many decimals to get down to something that's really small. So for n of air, we'll use 1.00. And if we're looking for n of the block, that'll be our n2, and that's what we're looking for here. And so if we take and we say n1 sine theta 1 equals n2 sine theta 2, then we can solve for n2. In here we can put our numbers. We can say 1.00 sine theta 1 is 45, so sine of 45, equals n2 sine of 33. And to solve for the n2 then, we'll divide both sides by the sine of 33. And I'll show you in a moment how to stick that in your calculator. So we're left with n2 here. So the way that that'll be set up is we'll say 1.00 sine of 45 divided by the sine of 33, and that will give us a number. It will be the n for n2. And so the way that you can do this is you'll just put it in just like this. You'll say 1.00 times, and you'll go sine of 45. In this calculator, I have to put a parentheses on there. And then I would just go divided by the sine of 33, put a parentheses on that back part there. Divided by the sine of 33. It didn't do it the first time. And when I do that, I end up with 1.298. We'll just say 1.3. It will be our answer, equals n2. And n values don't have any units with them. They're just a number. So by doing that, we have 1.3 equals our n2. Let's say you also wanted to know how fast the light was traveling in the block. And so because you know that n equals c over v, you could say that n of the block, so 1.3, I put too many there, 1.3 is equal to 3.0 times 10 to the 8th divided by v, and we need to solve for v. So I'll multiply both sides by v, and then I'll divide by 1.3. So I'll have 3.0 times 10 to the 8th divided by 1.3 will be equal to the speed of the light in the block. So if I take that, I stick it in my calculator, and I have 3 times 10 to the 8th, and then divided by 1.3. Here I end up with 2.3 times 10 to the 8th. It has it written out in long form here, but this ends up being 2.3 times 10 to the 8th meters per second. And so light in a vacuum is traveling at 3 times 10 to the 8th meters per second. Light, once it gets inside the block, there's more particles and more things to slow it down, and so it ends up traveling at 2.3 times 10 to the 8th meters per second. So still really, really fast, but not quite as fast as going through a vacuum. The other situation you might encounter is where you would have to solve for an angle. Let's say that you know that n1 is 1.00, and you may have theta 1 equals, I don't know, let's say 52 degrees. And we'll say that n2 is 1.25, and we want to know theta 2. Well, we still set up with what we have. n1 sine theta 1 equals n2 sine theta 2. And this time we'll have to solve for theta 2, so it'll have a couple of different steps in it. So the first thing we would do is to divide by n2 on both sides. And when we do that, we get n1 sine theta 1 divided by n2 equals sine theta 2. From there, we can put our numbers in there. We would have 1.00 times the sine of 52 divided by this n2, sorry, not sine, divided by 1.25. And that would still be sine theta 2. So to put those calculations in, you would say 1.00, you actually don't need that part, but we'll keep it in there, times the sine of 52, and then divided by 1.25. And when we do that, we end up with 0.6304 something something. So we'll say 0.630 equals the sine of theta 2. Well, that doesn't give us our final answer yet because we need to know what theta 2 by itself is. So to get that, we'll say the inverse sine, and in most calculators, it's pressing the second button or the inverse button, then the sine button. It'll show up like this, sine minus 1. And then we put our number in here, 0.630 will equal our theta 2. So we'll do that in this calculator. We'll say the inverse sine, so we'll go second sine of 0.630. And when we do that, we get that it is 39.050 something 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 degrees. And so we can just say 39 degrees equals theta 2. And so if you're not sure what you're doing in these, do it side by side with what I'm doing, because every calculator will be somewhat similar in that regard. And there's only two things that you can be solving for in these. You either have both ends and one theta and you're solving for the other theta, or you have one n and both thetas and you're solving for n2. Or n1, you're solving for one of the n's in there.